Welcome to a new edition of our research seminars at the IAC. Now in this beautiful room, players, because the aula of school. It's my pleasure to welcome Ángel Ricardo Plastino, who's coming from Buenos Aires, to collaborate particularly with Jorge and Nacho. And actually, I would like to invite Jorge to introduce our speaker today.
Okay, so it's really a pleasure to meet Ángel. A couple of words. He's by studies astrophysicist, but over time he has been doing theoretical physics in various aspects, like interpretation of quantum mechanics and statistical physics. And he's really an expert on the statistical physics of self-gravitating systems. In particular, our interest is to what extent that thing can be applied to understanding dark materials, of the behaviors of dark material. And he has a seminal paper, and that was really the starting point of the conversation, where he worked out for the first time what is the shape of dark matter of self-gravitating system that is in thermodynamic equilibrium. Okay? And so I'm going to stop here, say that he has been traveling, working all over the world, actually, in a very exotic place for us, which is South Africa, Brazil, and today he's going to talk us about well, complexity and to some extent relations with astrophysical things. So,
thank you for the introduction. Well, it's a pleasure to be here and collaborate with Jorge and Nacho. I would like to thank both Jorges, if you are Jorges, both Jorge and Nacho for the invitation and for giving me the opportunity to come here and collaborate with you. Okay, today I'm going to talk about a story about a proposal of complexity measure that was actually, in a way, started here in this institute, because this statistical measure of complexity was proposed by three Spanish researchers in 1995, exactly 30 years ago, which were López-Ruiz, Mancini and Calbet. And the third author, Calbet, was actually affiliated to this Institute of Astrophysics in Canarias, although I couldn't find it. Sorry, we're having some issues. Couldn't find anybody that actually knew him at the time when we were talking about 30 years ago. Jorge said that very sort of the name something. Okay. Well, why I am talking about this proposal about LMC? Well, because for various reasons. On the one hand, they proposed they made the proposal in the paper in 1995, but actually the first paper analyzing the measure itself and studying its basic properties was a paper that I done in collaboration with a researcher from Brazil, from Rio de Janeiro, in 1995. Sorry, in 1996. Well, why I decided to speak about this for. On the one hand, I think I'm probably getting older, and that means, and I like to go back to old papers of myself and see what happened after all those years. And also, I like anniversaries, and this is the 30-year birthday of this proposal by these people, and one of them proposed from here, and I am here now. So I thought it would be nice to make a kind of review of what happened with this measure after 30 years, and to discuss a few new points of view concerning this problem. So Let's first to put this thing in context. Well, you probably know that now there is a lot of activity in the field, in relatively new field, which is called the study of complex systems, the study of complexity. But among other things that people are trying to do is to establish quantitative measures of the amount of complexity that a system or a process has. But this study or this investigation and research on quantitative measures of complexity that are appropriate for the study of natural phenomena are actually at a very early stage of development, of exploration. Well, at least that is my personal opinion. Maybe if you ask people doing research in complexity, some of them would say that everything is clear, that everything is perfectly established, but I don't share that point of view. I think that, and many other people think that things are actually at a very early stage. So we are still exploring, people are still exploring and experimenting with very basic conceptual issues. For some people that are not working in this field, it may think weird or strange. Why a strange notion that trying to establish a measure of complexity? But it's good to remember that other quantities, basic quantities in science like energy, entropy, or information, that now seem to be absolutely clear, well understood, and unproblematic. Actually, those notions were clarified only after a long period of hard and tortuous conceptual development. We are now familiar with the final result, but people who started exploring some basic notions like energy, entropy of information, at the beginning, they had to do a lot of work on playing or experimenting with different formulations until eventually the final good definition, until these notions were finally clarified. I would like to again to set the context of this to make a very sketchy. Also, is my point of view and probably biased, but I will summarize a very sketchy way the chronology of the physicist involvement with the field of complex systems like this. I would say that the 80s was the heroic era of the pioneers, where a few isolated people in different places of the world starting to think about the problem of complexity from the point of view of physics. And the 90s were the period of consolidation, where the field started to spread, and people in the 90s started the expression complex system or complexity started to circulate more widely. And finally, at the beginning of the 21st century, the field of complex system expanded dramatically, and now it's a worldwide activity. You find, if you go to any university, basically in any place in the world, you will find research groups that devoted to the study of complex systems. One may ask why this field exploded in the 21st century, and I think it's anything. People think that it's because of computers, basically, and internet access to easy access to computing power and to massive amounts of data. And a few illustrative examples of each of the first period, the periods of the pioneers, is, for instance, this paper of Grasberger, well, it's a well-known research, very important leading researcher in statistical physics. And he was one of the first people to try to formulate a quantitative measure, or at least to explore the possibility of formulating a notion of a quantitative measure of complexity appropriate for study natural phenomena. And among other things, he formulated one of the basic properties that a measure of complexity or natural phenomena or natural systems should satisfy, and it is that it has to vanish when a system has large degrees of, or vanish or at least be very low for a system that has a large degree of order, but it also has to vanish for a system that has a large degree of disorder. And it should adopt its maximum value somewhere in between the total order and total disorder. And in that sense, he compared it with Kolmogorov's measure of complexity. Kolmogorov's measure of complexity is the most famous one, and the oldest one, and the most prestigious one. It's very important, very useful in information theory, for instance. But it does not it does not satisfy this let's say, boundary conditions that Grasberger proposed, that a useful measure for scientists should vanish as order, complete order, and complete disorder.
And axiomatic definition, or this is the
sorry?
It's axiomatic definition of complexity, or it's
you mean Kolmogorov?
No, the one by Grasberger. The fact that you vanish at the maximum disorder.
Yeah, well, you can.
That's not intuitive.
It's intuitive. He proposes it as an intuitive level, but eventually it is possible that someone sometime would formulate a set of axioms, and probably this would be one. And let me illustrate the idea. But with this nice, I think, illustrative picture it's taken from the paper of Grasberger. These three pictures. Here you see a completely ordered structure or a pattern, completely ordered pattern, like a crystal, for instance. And here you see a completely disordered pattern, for instance, the molecules of the picture of the molecules of the gas, for example. And this is something in between. So the idea of Grasberger is that from the point of view of the scientist, the complex pattern is this one. That this is not complex because it's very regular and very ordered. And this is not complex either because it's very disordered. You can't discern any interesting pattern here. And so he said, well, complexity should be vanished here, and should be maximum in somewhere in between, like this.
So it's like the number of lines in a code that you need to make a point.
That's related to what you mentioned is important. It's related to Kolmogorov's definition of complexity. Actually, Kolmogorov's definition of complexity is basically, roughly speaking, the size of the code that you have to write in order to generate the pattern. So, but if you use Kolmogorov's idea of complexity, then complexity is going to be maximum here in the completely disordered pattern. Kolmogorov complexity allows its minimum value here, because here you have lots of redundancy and you can, in very short code, you can generate that. And adopts this intermediate value here, but Kolmogorov's complexity is maximum here. And that's a point that is stressed by Grasberger in his paper, that from the intuitive notion of complexity that a scientist has, which would make complexity maximum here, Kolmogorov's definition of complexity is not used. I mean, as I said, it's very important in other contexts, but at least from this point of view, it's not useful. For a scientist, complexity should be high here, where you have interesting structures. And well, the same idea I'd like to illustrate with this Poincaré surface of section of a dynamical system, where we can see the transition to chaos. So here, low energies, you see in the Poincaré section that all orbits are regular, there is no chaos. As you increase the energy here, you start to chaotic orbits start to appear, and at high energies, chaotic orbits dominate. And so, if you, according to this notion of Grasberger, I mean, Kolmogorov's complexity again would be maximum here. But according to the idea of Kolmogorov, which is basically, by the way, shared by most researchers in the field of complexity, complexity should be maximum here or here, and should vanish here and here. So definitely it should not be. It does not. Kolmogorov notion does not satisfy Grasberger critique. So the Grasberger paper, as I said, is a typical paper of the 80s. And now we come to the beginning of the story that we want to do. And with the paper by López-Ruiz, Mancini and Calbet, which Calbet, as I said, was affiliated here to the IAC. And it's a typical paper of the 90s, where the field of complexity started to spread. And in this paper, they proposed a very simple measure of complexity that complies with the Grasberger criterion. The main motivation was to Grasberger criterion, to find a measure of complexity that vanish at complete order and complete disorder. And this paper turned out to be actually a very influential one. I mean, it's not the only measure of complexity. There are lots of them, but in its way, it played an interesting role. It had a remarkable impact in the scientific community. It has now it has more than 1,000 Google Scholar citations, which for you astrophysicists may not be much, but for a paper in theoretical physics, it's a lot. Particularly for what we might call a low budget paper, because it's a paper that does not involve expensive equipment or massive numerical computations or huge amount of data. It's only the proposal of an idea. So it's remarkable that it has aroused so much interest in many places. And among other things, it provided a testing ground for exploring the notion of complexity measure, the measures of complexity. Well, here I think it was interesting to see a very sketch of citation history. And in 1986, it had only one citation, which is this paper that I co-authored with Celia Anteniodo, a researcher from at that moment from the CDPF in Rio de Janeiro, Brazil. And well, in the next few years, it has a few citations. Here are the countries of the people who, and well, the citations were not locked until 15 years ago, but then it exploded, and well, and here we go then to the idea, the basic idea of complexity, which in a sense I think is the most simple possible definition that complies with Grasberger criterion. The idea of them is to assign a measure of complexity to a probability distribution. Maybe a discrete probability distribution or a continuous probability density. And the idea is very simple. They proposed as a measure of complexity a measure which is a product of two quantities. On the one hand, Shannon entropy of the probability distribution, and on the other hand, this quantity which they call disequilibrium. So you can directly see that this measure C of complexity vanished in the two cases of complete order and complete disorder. In terms of the probability distribution, complete order can be identified with certainty. When one probability is 1 and the rest is 0. And complete disorder we can identify it with equiprobability. And so, in the case of complete order, the entropy vanishes, and in the case of equiprobability, this disequilibrium D can be regarded as a kind of a quantity that tells you how different is your probability distribution from equiprobability. And okay, so this was the LMC proposal in 1995, and the first paper that's investigated some properties of this proposal. By the way, in this paper they only make the proposal of the measure and provided an illustration. They illustrated it with, they applied it to the logistic map, and they computed a measure as a function of the logistic map involves a parameter that for certain values of the parameter you have regular orbits, for other values of the parameter you have chaotic orbits. They computed it as a function of the parameter, and they saw that the maximum, it adopts its maximum value precisely at the edge of chaos, at the point where you have the transition from regular orbit to chaotic orbit. So that makes sense. Most people will agree that if you have to identify some points in some regimes in the dynamical system which can be regarded as complex, are precisely those that are at the edge of chaos. So in that, at least in that example, the measure worked. Yielded results that made sense. And then this is the first paper which is actually studied the properties of the measure, which the LMC in the 1995 paper did not. And well, on the one hand, in this paper we actually computed which are the probability distribution that maximizes the measure, which LMC did not. And they studied some basic properties, but our paper was, in a sense, critical. I mean, on the one hand, when we determined the probability distribution that maximized the LMC measure, we were a bit disappointed because we found that the probability distribution that maximizes the measure was actually very simple. It was, well, one state with high probability, and all the remaining n-1 state with low probability and all with the same probability. So you have a sea of states with all with the same probability and just one state with a huge probability. That is the kind of probability distribution that maximizes the LMC measure. And on the other hand, we pointed out that the measure did not, the LMC measure did not comply with some requirements that intuitively we thought a complexity measure should satisfy. In particular, we showed that the LMC, in the continuous case, the LMC measure was not invariant, for instance, under change of scale. We thought that a complexity measure should be invariant under change of scale, because just changing the scale of your probability density should not affect the amount of complexity, because it's a simple transformation. And on the other hand, we proved that it is also not invariant under replication. I will come back to that later. Our paper, to some extent, then established the agenda for other people that reconsider the LMC proposal and in turn proposed variants of the LMC idea that, among other things, were designed so to cure these problems that we found in the 1996 paper. That is, other researchers, including LMC themselves, addressed these issues and proposed new versions of the LMC measure that were improvements and that solved some of these problems. So what we thought in almost 30 years ago when we wrote this paper was that the LMC proposal was interesting as a testing ground for exploring the concept of a measure of complexity, but that the measure itself, in a sense, would not survive because we thought that if it had these undesired properties, the measure was not an appropriate one. I mean, it turned out we were wrong. I mean, in the sense that we thought that with this paper it was basically the end of the story, but we were wrong. I mean, we in a sense were right in the sense that the LMC measure is an interesting testing ground for exploring the notion. In that sense, I think we were right, but we were wrong because it was not at all the end of the story. Lots of people continue to work in and to do interesting things, and I am very happy. I am very happy that we were wrong in that sense, because, well, it's much more interesting that it turned out that these problems could be solved, and the story continues. Okay. So, as I said, many people, including some of the authors of the original LMC proposal, proposed new measures that solved some of the problems. So this is another one that was proposed by Catalan, Garay, and López-Ruiz almost 20 years ago, and again has the same structure of a product, but it's something quite interesting that with a little change, that is, instead of putting here the entropy, to put the exponential as the entropy, that little change solved various of the problems that we pointed out in 1996. In particular, this new definition is invariant under rescaling, and under particular interpretation of the replication. I would come back to the problem of replication later. And then there is an extension of the idea of this paper of 2002, this paper of 2009, again by López-Ruiz and collaborators. And this extension is defined in terms of Renyi entropy, and it also satisfies many of the requirements that we pointed out in 1996. In particular, this generalization in terms of Renyi entropy is invariant under Ricardo transformation and an interpretation of replication, but satisfies another condition that has been basically overlooked in this story. I mean, we didn't thought about that issue in 1996, and it is not mentioned in any of these later papers where they propose improved versions. I think in the context of complexity measures, LMC-like complexity measures, this concept has not been explored, and which is the concept of composability, which I explain now. The idea of composability is the following: that a complexity measure, I think, should satisfy the following condition: that if you have two completely independent systems, A and B, you can compute the complexity of A, CA, and the complexity of B, and you get another number, CB. But you can always regard both systems as a single entity, as a single system. And the idea of composability is that the entropy of the two systems, when you regard them together as a single entity, it should be possible to compute that in terms only of the complexity of A and the complexity of B, without knowing more internal details of the systems. Yeah. As an illustration, suppose you have a system A here on Earth and system B far away in Andromeda and completely independent. And system A has an amount of complexity CE, and that far away thing in Andromeda has complexity CB. Composability would mean that if someone asks you what is the complexity of both when you consider them together, well, you should be able to compute those two things without knowing the internal details of E or B. If you know the complexity of CE and the complexity of CB, that should determine the complexity of the whole. That's the idea of composability. Composability is a concept that has not been discussed in terms of the LMC measures of complexity, but in recent years has been discussed a lot in the context of entropies. It is regarded as an essential property of an entropic measure or an information measure. Well, as an example, you can, if you're interested, you can see that paper by Enciso and Tempesta from Madrid, where they make a summary, kind of review of composability for entropies. It's the same idea that if you have two statistical independent systems, the entropy of the whole should be a function of the entropy of each part, without any need to see in detail what A and B have inside. Okay, and it's a very from these studies of composability and entropies, it has been established that composability is a very strong constraint on possible forms of an entropy. If you consider a very general form of entropy, that's a function F of the summatory of other functions evaluated in the probabilities. Well, there are technical details that I don't put here that F and H has to satisfy some requirements, but leaving aside that, the general form is that. It is possible to prove that the only entropic form that comply with composability has this form. It has to be a function of the sum of the power of the probabilities. So that means that composability is a strong constraint. And paradigmatic examples of entropic forms satisfying composability are ready entropy, which is the most general additive entropy. And well, additivity is a form of composability because you obviously see that if you have two independent systems, the entropy of the whole is just the sum of the entropies of each part. You don't need to know any details. And another paradigmatic example is Sally's entropy, which is the most general composable trace form entropy. Trace form means entropies in which this F is the identity function. That is, you have no F. If you have only the summatory of a function of Pi, then basically the only composable entropy of trace form entropy is Sally's entropy. And of course, Shannon entropy is also composable. It's a particular case of both Sally's and the Renyi families. Okay, that's for entropy. But going back to complexity measures, if you have, this is again the original LMC proposal, which is not composable. It does not satisfy composability. And if a complexity measure is not composable, some weird things happen. For instance, that you may have two statistically independent systems, which both each one individually has complexity 0, but when one regards them as a single thing together, they turn out to have a considerable amount of complexity. So that's, I think, quite counterintuitive. It doesn't make much sense that you have A has zero complexity, B has zero complexity individually, but when you consider them together, you have a finite amount of complexity. Okay, that thing happens if the measure does not satisfy composability. But the good thing is that this generalization of the LMC idea proposed by López-Ruiz and collaborators in 2009, I mean, they didn't mention that point in their paper, but it turns out that version of LMC does satisfy composability. Well, this is a summary of all the nice properties of this 2009 version, including composability. And now let's go to the problem of invariance under replication. Also two pioneers on this field of from the 80s, the era of the pioneers, Lloyd and Pagels. They also have their own measure of complexity, which is completely unrelated to the LMC one. But in that paper, they pointed out to another constraint that is at first sight makes a lot of sense. Another constraint that the complexity measure should satisfy, which is invariance under replications. The idea that they have is that the following: if you have a system A that has a certain amount of complexity, and you construct an identical replica, statistically independent but identical to A prime, let's call it, but identical, then they say the entropy of the complexity of the world does not increase. Just by replication of a complex system, the complexity of the world doesn't increase. So let's say if you have a work of art, fantastic work of art like Michelangelo, which probably has a lot amount of complexity, and you with a 3D printer or a scanner and printer, you make an exact replica, the complexity of the world doesn't increase. That's the idea of LP.
But sorry, identical meaning what you just said, or do they have the same probability distribution function?
The same probability distribution function, and the statistically independent. Yeah. That's it. So they proposed that notion in 1988. Well, unfortunately, none of the LMC proposals, the different versions that I mentioned, satisfies replicability in the sense of LP. They satisfy another kind of replicability, but the basic one, the LP one, is not satisfied. Now, if we now compare the LP notion of replicability with the notion of composability, we can summarize LP replicability with this equation that the complexity C of A plus E, where by A plus E I mean two identical but statistically independent systems, the complexity of that whole thing should be equal to CA. And that turns out to be difficult to reconcile with composability. That is, composability, which I think, from my point of view, makes a lot of sense for a complexity measure. And on the other hand, LP invariance and the replication also make a lot of sense, but they seem to be incompatible with each other. So here we have at least within the frame of the LMC-like measures. So we have a tension here between two properties that intuitively makes a lot of sense for a complexity measure, but they seem to be incompatible with each other. So I don't know what can be done here. One, I would think that composability is more fundamental, more important. So one possibility is just to give up the requirement of LP invariance. And the other thing is to contemplate that the basic idea that started with the LMC paper in 1995 of assigning a complexity measure to a probability distribution, maybe that basic idea is problematic. maybe with the probability distribution is not enough to assign a complexity to the system. Maybe you need to know other properties of the system, other features besides the probability distribution. And in this sense, we should remember that sometimes there are intuitive notions that at first sight seem to make perfect sense, but under close inspection, they turn out to be problematic or even inconsistent. So, okay, that's an open issue. Well, as I said, from the late 90s and beginning of the 2000s, the attention of researchers that were interested on the LMC-like proposals or complexity measures shifted from the consideration of the basic conceptual issues to applications. Lots of people started to just apply the measure and see what happens, and it turns out that there are lots of interesting results. Well, it's impossible. There are hundreds of papers, so it's impossible to summarize here. But among other, I like very much this recent paper by Here and Ruiz, where they apply the LMC complexity measures to the study of planetary systems, and they find nice results. I mean, it's an observational. This paper deals with observational astronomy. Well, it seems that they work with results from Kepler, and there are some planetary systems where, well, it is more easy. Well, you know that much better than me, that it is much easier to detect planets that are close to the stars because you study the transits, okay? But it's difficult to get information about planets that are far away from the star. And so people are want to study the structure of the inner parts of a planetary system to try to infer something from what happens far away. And what these people found is that they propose something that is gap complexity, which is basically the LMC complexity applied to the distribution of gaps between the orbits of the inner parts of the planetary system, and they found out that quantity, that gap complexity, is a good predictor of the presence of the giant planets that in the outer parts of the planetary system, which are difficult to detect. And they found that high amounts of complexity usually coincides with the presence of these faraway outer planets. So that's an example. There are not many applications of astronomy, but to astronomy of the LMC measure, but this is a nice recent application which looks quite interesting. And as an illustration, just as an illustration of a kind of applications to other completely unrelated problems, I would like to mention this research, to illustrate just an application to music by these researchers from Brazil, which they wrote a very interesting paper where they apply the LMC-like measures to the classification of musical channels. They compute the complexity on the record of a song or a piece of music, and they plot that in a plane where in the horizontal axis you have the entropy, and in the vertical axis you have an LMC-like measure, not exactly LMC, but close relative also based on the product of quantities. And you can see how the different musical styles are distributed in this plane. And well, if you compute let's say the center of mass corresponding to each style, yeah, there are.
So the more to the right, the less complex, or the more complex, or it's in the middle.
Complexity is
Complexity.
See.
What is HS?
Entropy.
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 Complexity.
Yeah. I find it nice that classical music, jazz, and tango.
Reggaeton.
Eh?
Reggaeton.
No.
Yeah, you should put the exactly with the number of downloads people. The number of listenings.
Yeah. Good idea. They should correlate it with the number of listeners. Yes.
And excuse me, what's the difference between Pan Jose and B? So could you tell us?
Yes. On one side, they use a pattern. The amplitude, just the amplitude of the signal. On this side, they use the intensity, which is just the square of the amplitude.
Okay. So it's just a transformation in a sense.
Yes.
Okay.
Yeah. It's basically the same data, and it's only
But complexity here means what? So
I
you
don't-
don't know how.
no. It's just a measure applied to this, and they see what happened. Yeah. That's the basic now. The basic, let's say, conceptual issue that this LMC family of measures, people have applied them to lots of things, and in many cases they find interesting results, and that makes sense. But if you ask me what does it really mean, that's something that I can explain in words. I don't know. It's just a measure that complies with some properties that one find that intuitively a complexity measure should satisfy. But to explain what it is, it's a difficult question. And that it's related. That's a basic question. It's related to two other. There are, in particular, the first one, that what is lacking is an operational interpretation of the LMC measures. That is, for instance, with the Shannon information measure, you can say, okay, you can study the mathematical properties of the expression, all works very nice, but it means something very concrete. It gives you, roughly speaking, it measures the size of a memory device that you need to store data. Yeah. And so here there is no, so far, as far as I know, to the best of my knowledge, there is no operational interpretation. It would be nice also to have an axiomatic characterization of the measure, which there is no set of axioms that there is consensus that should describe. Another question is, what kind of dynamical, to study dynamical aspects of the LMC measure, what kind of dynamical processes naturally leads to distribution that optimize this measure under suitable constraints? That's also there is some work. López-Ruiz himself have done some illustrated the behavior of the measure in some dynamical systems, but there is no basic idea of a dynamical system that naturally leads to the increase of this measure, or to the optimization of this measure, and probably under constraints. We have done some exploratory, but is at a very early stage, to formulate a Fokker-Planck-like equation that leads to the constrained optimization of the measure. And we obtained one which has some similarities with other probably with other evolution equation that has been studied in the literature for different reasons. For instance, this one, where you have Fokker-Planck equations with two types of diffusion together, one linear and one non-linear, but okay, that's a very early stage. So okay, just to summarize the LMC proposal at 30. Well, I think the LMC proposal advanced by López-Ruiz, Mancini and Calbet 30 years ago constituted an interesting conceptual experiment on the notion of complexity. I mean, if it's going to last or not, if people are still going to be discussing the measure in 50 years, it's impossible to know. But it played an interesting role as a concrete proposal where we can actually check different ideas regarding complexity. And it stimulated hundreds of research efforts all over the world, the LMC paper. But right now, there are many basic issues that remain to be explored. And at the fundamental level, we seem to have more questions than answers. So we can say, to close, that the LMC conceptual experiment still goes on. And thanks a lot for your attention.
Yeah, thank you for your very nice comprehensive talk. Questions or comments?
So, imagine that we were finally successful on defining complexity. So one of the things.
Sorry, I didn't hear.
So imagine that we were having finally the definition of complexity that we were referring to satisfies all these properties that you are asking for. So what would be the use of having that, for example? So that would be applied to a given system and know whether it's very close to the maximum complexity it can have, and therefore we would like decreasing it because it's dangerous or it's unstable, or I'm thinking of very big code, or so you get the point. No? So
yeah.
you would like optimizing, but you don't want to have the most complexity system possible, right? Not necessarily.
It depends on what, but I mean, if one is very ambitious, I think to have first of all, I think again that as I said at the beginning, that the notion of a measure of complexity is only at the is still, even that a few decades already passed, it is still at the very early stage. It's still at the stage of exploring very basic issues. It may happen that a single number is not enough to characterize the amount of complexity of the system. Maybe you need some more, I don't want to use the word more complex because it's more elaborate mathematical object that is not enough to have one number. So, but by the way, if you think that this is, if you think we are to try to define the measure of complexity, there are more weird things that are now that are related to this and are being explored in the literature. I mean, by very serious people which are, for instance, quantitative measure of consciousness, and which is actually closely related to this. And well, the usefulness would be plenty. I mean, for instance, to study the emergence. I mean, in a very ambitious, in the future sense, for instance, to study the emergence of life in the planet and see how to see how complexity arises and grows, and to study laws. Maybe the evolution of complexity with time also follows laws that we don't know yet.
You mentioned that there are applications to astronomy. There are, I mean, could you comment on some of these applications in particular? Is someone tried to measure like the complexity of the universe, how it evolves with time, these kind of things?
Let's see. As far as I know, with this family of LMC, when I say LMC measures, I mean these that are constructed as a product. With this family, as far as I know, no. But I know at least
it makes sense.
I don't know. I don't know. But I know at least one researcher who tried. He did some work applying the Kolmogorov measure of complexity in the context of cosmology. Is maybe you know Vahe Bursarian is originally from Armenia, but then he had a position for many years at Rome, La Sapienza. He applied Kolmogorov's complexity to some problems in cosmology. And I don't remember much more details. But,
Sorry, what is the name?
Bursarian. I think it's Vahe, the first name, B-A-G-E, something like that.
I was wanting to look for the paper.
Yeah, if you put Bursarian complexity, Kolmogorov complexity, you probably will find. I think one of his papers is in EPL, Europhysics letters. Yeah.
Just as one question, and you showed us this how different music genres were compared.
Yeah.
But then going to astronomy, do you think that it could be possible to compare, for instance, the dynamical behavior of, for instance, globular clusters as different objects and give some information on complexity of these systems? Would it be possible to compare them? What would you need to make systems be comparable?
Yes. Well, the first step, since the LMC family of complexity measures are things that assign the complexity measure to a probability distribution or to a probability density, I mean, if you want to apply it to a particular kind of objects, the first thing is to map to first you have to get a probability distribution or a probability density from those objects. That is somehow to map those objects into a probability distribution. And then you can compute the measure and see what happens. In general, all the applications they compare complexity measures of things that are in the sense of similar, that are belong to the next, let's say, to the same hierarchy of like music. They compare music with music. I mean, I don't know if you can compare, let's say, music with literary works. But if you are within the same family of objects, in principle, you can, and like these people who study planetary systems. Yeah.
Okay, we don't have any more questions. Let's thank.
It's something. So, and fractals, I'm sure that they have been studied. They are complex. They are not. They are very simple to write in a code.
Yes.
But they look crazy. So is that thing complex according to this?
Well, usually they are regarded as complex objects. Yes. Yeah. Maybe not in the sense of Kolmogorov, but yeah. But it depends. Fractals can be lots of things. Yeah, it depends.
Sorry, to also got relation to this the Kolmogorov complexity measure. Does that fulfill all the criteria that you were thinking about, like this composite bands, this set of replication, and so on, or it also fails to fulfill this criteria?
I haven't think. I don't know if it satisfies composability. I'm not sure, but I guess I would. If I have to bet, I would think that probably it satisfies composability.
All right, so let's thank Ángel.
Sí, eso está súper orgulloso de
Ay, seguí las órdenes.
Pues